The exam will be 4 questions, 50 points. In case you wonder why that's the case, it's because the first question is a bit long. I think it has like 7 or something like that multiple choice instead of 3 to 4. That's why the first question will be 20 points. So that's why it's 50 points total. The duration is 70 minutes. So again, the midterm is usually the number of points plus 10. Since this is the final exam, it will be the number of points plus 20. So 70 minutes. So basically, we'll start at 5 p.m. We won't start at 5 p.m. exact, probably like 5:03 or something, just in case people are walking there. But we will start when the class starts. So the exam will end probably around like 6:15, something like that. Okay, so the exam starts early, and then you do not have to stay for the entire time. After the exam is finished, I'll take it to the department printing room to scan the exams and upload it into Gradescope. So please arrive on time at 5 for the exam next month. Don't skip the class for next Monday. That's not the thing you want to do. The exam is cumulative and cover all material from the course, which means the final exam includes material after the midterm exam and the material from the midterm exam. So that's the scope. So basically everything, because it's a cumulative exam. Just like before, you can use 1 page of notes, single or double-sided, and also you can use scientific copy. So that's the ideas for the exam. So because we have 3 free response questions, question 1 is multiple choice, question 2 will focus on the material from the first midterm, question 3, the second free response, will focus on material from the second midterm, and question 4, the last question, will focus on the material after the 2. So basically, the 3 free response covers 3 periods of the class, and the multiple choice spans the class. Okay. In case you wonder what the first question on the exam is, it's going to ask you about the assumptions for the error terms. Absolutely. It's very similar to the first midterm, but that's the first question on the exam. Okay, so any other questions regarding the logistics? And as usual, we have the at the end of the semester, if at the end of the semester we will I would modify the score so that the median score is at least 90% or at least 50%, at least half the people will get a deal. So that one's still there, so that would alleviate the stress a bit with the final exam. And then after like 6:15 on Monday, there's nothing there. You can just go off and enjoy the holiday. Before that, one thing, I'll send out a follow-up announcement later today or early tomorrow. For every group of the presentation, please upload your slides onto Gradescope. So I'll create an assignment tonight and then I'll send out an announcement. Each group has to upload once. There's a group assignment option on Gradescope. So I get to keep a copy of your presentations as a record for assignment scores. So it's not to be graded or anything like that. It's just that I do a copy of your presentation as a record. So I'll send out an announcement tonight, and then we'll that will be due. Let's make it due next Wednesday, so 2 days after the final exam. Good. So today I want to cover kind of all these things here. So the first thing is the epsilon assumption. And as usual, the first question we'll ask you on the error terms. And the 4 things that are important are they're normal, they have expectation 0, they have same variance, and they're independent of each other. And also, the error terms and the independent variables are independent. Okay? Because otherwise you can just absorb an epsilon into the exam. There's no need for error terms. Also, the error terms cannot be reduced to 0 because otherwise, otherwise there's just no need for regression. so the error terms they follow normal distribution with expectation 0, but they cannot be reduced to exactly 0. So that's a key idea for the error term. Yes. Yeah, right. It's yeah. Okay, so any questions? Okay, so the next thing is this new concept called the ANOVA command. So recall, we don't even need to recall because this is the key line of our command from the semester. We're in the autos data set, and we're trying to regress miles per gallon on horsepower, acceleration, cylinders, and displacement, so 4 variables. And the command is, of course, linear model, and then MPG tilde, the whole thing data equals column. Previously, we have seen summary of regression. The summary of regression gives each row, it's basically everything else in the model. Should I include the extra variable? Today's new concept is called ANOVA regression. Okay, so ANOVA. What the ANOVA does is that ANOVA does stepwise test. Okay, I'll explain what this means in a sec. But basically the idea here is in the ANOVA command, the horsepower, acceleration, cylinder, and displacement ordering matters. Okay, I'll explain why it matters on the next slide. So basically, the format for the final exam will be similar to the midterms. I will give you the R command, I will give you the R command, especially the result, the output from the R command, and then ask you to make interpretations based on those results, okay, just like a midterm. So the result will look like this. So this is the ANOVA result data. Now I wanna, I wrote something here, but I'll explain exactly what they are. But if you recall in the summary command, the p-value when it says after the raw horsepower means, should I have the model including only intercept, acceleration, cylinder, displacements, or the alternative is my model includes intercept, horsepower, acceleration, cylinder, and displacement. So the two models has only a difference of whether you should add horsepower in addition to everything else. Now in ANOVA it's different. How is it different? The step and horsepower. There is nothing mentioned in the things below, and nothing mentioned acceleration, cylinder, displacement. Okay, so let me move. So I'll post it tonight. So. Next, what is the orange 1.124 10 to the negative 7 power? That means, should my model include everything before acceleration versus should my model include everything before and including acceleration? So no hypothesis here is that model has intercept horsepower, so everything before acceleration, whereas the alternative is model include intercept horsepower and acceleration, intercept horsepower and acceleration. Okay, so basically here what we're doing is we're doing stepwise test. The first rule is not the intercept versus intercept horsepower. Second rule is intercept horsepower versus intercept horsepower acceleration. And just let me ask, what is this 2.828? Sorry, my brain is already out of this world. What is this 2.282 10 to the negative 11 power in the cylinder? Intercept horsepower, exactly, that's no hypothesis, correct. And then the alternative are intercept horsepower acceleration and very good. So, in case, so any questions regarding how to interpret the results? Good. So you see the difference between ANOVA and summary. Summary is the order doesn't matter, but ANOVA the order matters a lot. Right? If horsepower and acceleration are switched, the result will be completely different. But in summary, if horsepower and acceleration switch, nothing happens. The result stays the same. So that's the key difference variable. Now the question is, what might be one application of this? So you'll see many applications of this. I think we discussed 4350, but one application for ANOVA results is that you can use this table to do sequential hypothesis testing. Basically, you start with nested models. The first model is intercept. The second model is intercept horsepower. The third model is intercept horsepower acceleration, so on and so forth. And you stop at the location when you encounter an insignificant p-value. So I'll write that down in a second. So basically, we go through each line and then go from top to bottom. Every time we compare two nested models, nested means the alternative model, the null hypothesis model is a subset of the alternative model. And the alternative is null model plus one hypothesis. If the p-value is greater than the significance level, then what we say is the hypothesis test is insignificant, so we select a smaller model. Otherwise, we continue with the next test that will augment the variable. So we'll see an example after this slide. So let's look at an example when, significance level is 5%. Okay. So the first pair is the null hypothesis that the model contains only intercept versus the alternative model that the model consists of intercept and horsepower. So intercept model contains intercept and horsepower, the first variable. So that's the first comparison that we do, and the result is given by the p-value in the first row, which is less than 2.2 into the negative 16. So the result is p-value is less than 2.2 into the negative 16, which is way less than the significance level of 5%. So what is the result? The result is we reject the null hypothesis. We reject the null hypothesis and continue with the next pairs test. Okay.
Can we just change the color of the print? It's really hard to read.
Oh, what color? Maybe to, let's say,
Just not the like super light blue. Anything else?
let's see, maybe orange.
Yeah. Is that?
Oh, that's red. Yeah.
That's.
Oh, it's even worse, huh? Okay. You don't want to put red because red is
Dark blue would be fine, just not the super light blue.
This one?
That's totally fine.
Okay, cool.
Thank you.
Sure. So again, if p-value is significant, we move on to the next pair. If p-value is insignificant, we stop and go to the move. That's how this works. And now let's go to the next pair. The null hypothesis now is a model contains. Does someone want to say what should the second hypothesis test be with a p-value 1.124 and 10 to the negative 7? Yes. Yeah.
So the null hypothesis would be the model consists of intercept and horsepower.
Exactly.
The alternate would be model consists of intercept, horsepower, and acceleration.
Thank you. That's exactly the case, right? So model contains intercept, horsepower, intercept and horsepower, and the alternative. The alternative is model consists of intercept, horsepower, and acceleration. And the And now the p-value is 1.124. So now the p-value equals 1.124, 10 to the negative 7th power. Okay, which is again way less than the significance level. So we reject the null hypothesis and continue with the next pairs. Okay, and then you know, after all the testings, because all the p-value here are less than 5%, so what we do is we go with the full model. Okay, so everything is selected. So after the testings, the full model consisting of intercept and all other variables are selected. Good. So any questions? So if all the p-values are significant, you just select the full model. So next we will look at a few more seconds. Yes.
So this annual commodity set was going to be the new thing that's going to be on the file.
Yeah, exactly. So it's going to be compared to the yeah, it's going to pop up somewhere. I just said this way. Okay, so you know, just to make sure that we get sufficient practice, what happens if the significance level now becomes 0.1%? So if the thing becomes 0.1%, the first horsepower is again significant because the p-value is less than 0.1%. So we go to the next pairs testing. The acceleration part is also significant because 10 to the negative 7th power is also less than 0.1%. The cylinders part is also significant because 10 to the negative 11th power is also less than 0.1%. But what is not significant is this 0.003. This thing is actually larger than 0.1%. Okay, so all pairs will be significant until we reach the pair where the null hypothesis is intercept horsepower acceleration cylinders okay, and then the alternative is intercept horsepower acceleration cylinders and displacement. Here, the p-value is 0.0035, which is larger than the significance level of 0.01, which means we fail to reject it. Okay. So the conclusion here is we select a model with the things in the null hypothesis rates inserted. So we select like a model with intercept horsepower, accelerated cylinders, and not displacement. So whenever we meet something that is not significant, you select the null model and stop because it's sequential testing. You stop it to move forward. But if all the p-values are significant, we go with it. Horsepower acceleration cylinders, intercept horsepower acceleration cylinders. Very good. Any questions? Yes.
So in other words, can you say intercept as beta 0 horsepower as beta 1 and so on?
Yeah, you could do that, right? So the null hypothesis in the start will be like beta 0 is unequal to 0 and all the other betas are equal to 0, whereas H1 is beta 0 equals unequal to 0 and beta 1 unequal to 0. So that also works. Very good. Other questions? Yes.
The way I understand it, it seems to be kind of minimized model size.
Exactly.
What if, like, displacement, like, is the second predictor we look at, and we don't look at the other one as significant?
Exactly. It's completely possible if you switch the. That's the thing, right? That's why I emphasized in the command the ordering here matters, or the who's on top actually matters. Right? If you move, for example, displacement on top of acceleration, the p-value might actually be significant. So that's why sequential testing is also sort of like a review. Very good. Good. So the conclusion is we select a model with intercept, horsepower, acceleration, and cylinders. Very good. So next thing we want to consider are the ridge and lasso regression plots. Okay, so those plots, and those are the plots. So let me run this on this computer because I haven't updated my thing yet. So. Okay, there you go. So this is the, Good. In case you wonder why the plot looks a bit different, this is when I updated the other computer to get version 10's graph, and the difference between version 10 and actually this is not the lasso regression plot. This is the ridge regression plot. So the reason why they look different is because this is version 10 and they use the negative log of lambda as opposed to version 8 positive log of lambda. So kind of the way how you read it is different. The variable 14 here, so again, let me use the darker color. So variable 14 is the league categorical variable. League categorical variable, whereas the variable 7 is years. So 7 is years. 7 is years. So it's a numerical variable. So the different numbers, they correspond to different variables. On the exam, on the exam, I'll make a subset of the variables. So you can't have 19 of them, which is too much. For example, on the exam, there will be like 5 or something like that. Okay. And then I'll explain that this number is this variable, that number is that variable. So it will make it very clear on the things. Again, the x-axis here is log of negative log of lambda. So number 1 is negative, and also notice the log, because they can get big. And then for example, if we look at the part where it says 19 here, so let's say this 19 means when log of lambda equals to 10, or similarly when negative log of lambda equals to negative 10, they're the same in terms of size. There are 19 coefficient estimates, or we should say slope estimates, because it's in addition to intercept. So there are 19 slope estimates being non-zero. So the 19 just means how many coefficient slope estimators are non-zero. So for example, what we will see is some statements, for example, the question could ask is, when negative log of lambda equals to 5, or alternatively log of lambda equals negative 5, the coefficient estimates for the league variable is around 120. Okay. Another statement we can make is that, for example, when log of lambda equals to 0, the estimate for the coefficient estimate for variable 7, which is years, is around negative 20. So those are some things that we need to be able to identify for the exam. And similarly, this 19 means when log of lambda equals to 10, there are 19 slope coefficients, or basically all the slope coefficients who are non-zero. That's the characteristic for which everything has shrink to 0, but not exactly 0. Any questions? questions regarding the interpretation. It's the same as the class one deciding not to flip them. I have no idea why they decided to flip it, but since they flipped, we'll just use it. Questions? Good. So now let's look at the lasso plot. No, this is not the lasso plot. Let me get the lasso plot from the other. Okay, now one very important thing with the lasso regression is that now you realize when negative log of lambda is equal to a small number, basically when log of lambda itself is equal to a large number, the number of coefficients being non-zero is set to exactly the value of 0. So when you decide, when you see between real and lasso, real here is always like 19. The lasso is to 0 equals negative. Let me write that down. The idea here is, let me again use the darker color. So the idea here is when log of lambda, what is this? What is this? Okay. Let's refine. When this is ridiculous. When log of lambda equals to 20, okay, or negative log of lambda equals to negative 20, there are all slopes estimates are exactly 0. Okay, so the 0 on the top means when the log of lambda equals to 20, all slope estimates are exactly 0. So that's a characteristic for a ridge. And then, for example, let's look at this 3 right here. This means when log of lambda equals to 5, again, negative log of lambda equals negative 5 is log of lambda equals 5. Only 3 slopes are non-zero. Okay, and we can see the 3 slopes here, but we're not going to test like eyesight to look at the people things. So on the exam, again, I will select a subset of them, for example, like 4 or 5 of them, and I'll clearly read each school. So otherwise, it's impossible. I mean, who can read this, right? It's too much. So, then on the software, we can always zoom the graph, but okay. So let's look at this variable. Let's see what it is. This one's variable 14, which is Lie categorical variable. So this 14 is Lie categorical variable. What we can see is when the log of lambda is small in absolute value, the estimate is very large in absolute value, but when log of lambda increases, the absolute value of the coefficient is decreasing. Okay, so for small lambda, and again, small lambda means on the right side because they switch the order. Okay, so small lambda means on the right side. The estimator, the slope estimator is large in absolute value. Is large in absolute value. Okay, but when for large lambda, it shrinks to 0. In fact, it shrinks to 0 around the location where log of lambda equals to 4. So yeah, just make sure, negative log of lambda equals to negative 4 means log of lambda equals to 4. And then lambda, of course, is exponential e raised to the 4th power. Questions? Cool. So next, let's look at the cross-validation plot, and again, no, actually, let's do the other one. Let's do the last one. Yeah. So this is the last one. Good. So in version, again, I'll put this as version 10, so version 10. In version 8, the plot, what we did was we selected the lambda, we selected the location with the smallest lambda. Here, what we do is we select the location on the right side. Okay, the reason why we selected this on the right side here is because the right lambda here, negative log of lambda, negative 2.2, is a lot smaller than this guy right here. So this guy is +1 standard deviation. But since the scale has been reversed because of this negative sign in the front, now we read the thing from right to left. Okay. So you don't have to memorize whether we read the thing from right to left or left to right. We just find the location where log of lambda is smallest. Not negative log of lambda is smallest, but the log of lambda is smallest, which is this location right here. Alternatively, you can also see where the red dot is the smallest, and that is the definition for the optimal lambda. And that here the cross-validation error is a lot smaller than that right here. So the answer should be around this location right here. So let me annotate it here. This is the location for, this is an absolute disaster for this, so this is a location for optimal lambda. Now, of course, this means that the negative log of lambda equals to around negative 2.2. So lambda here equals e raised to the 2.2 power, which is around around 9. So this optimal lambda actually comes out to be 2.2. Only 2.2286. Yeah, so the optimal lambda is around 9.287. Now, on the exam, there's no way you're going to know that this location is going to be 2.2286. So there's going to be a number around this negative 2223, and there's going to be a number that's far from this value. It's not going to be close because it's impossible. I mean, if I give you this dotted line to ask you this dotted line that corresponds to negative 2286, if you can read that, you don't need to take this class. It's just impossible. Okay, so there will be around a negative 23 on the exam, and then probably there will be a number here around negative 5, and do not select a negative 5 because the contract is reversed already. So you want to select the one corresponding to the smaller number. On the exam, if the graph doesn't look as nice as this, I will trim the graph so the graph only shows, for example, this area right here. Okay. The reason why the graph will be trimmed is that if the graph has a large spread, for example, going from negative 10 to 10, it's impossible to fit the graph on the exam. So basically, the graph will now only run from, let's say, negative 5 to negative 1. So you only see this area in the center. But again, the ordering will be negative log of lambda, so you select the one on the right side. And also, in case you don't want to think about that, the optimal location is always the one with the smallest mean square error. So whoever the red dot is lowest, that's going to be the location. Okay, and then what does the 10 on the top mean? Okay, so the 10 on the top means. So the 10 here means, let's write this on the left. So this 10 here means at the optimal lambda value, exactly 10 slopes are non-zero. So at the optimal lambda value, exactly 10 slopes are non-zero. So 10 is the model size. E raised to the 2.2286 power is the optimal lambda. So that's what it means. For example, this 0 here just means when log of lambda is around 5.5, there will be exactly 0 coefficients for non-zero. Everything is 0. So the model only has the slope. Sorry, only has the intercept. Sorry. So again, To find the value of optimal lambda, you look at this guy right here, the negative value is equal to negative log of lambda, so the value is e raised to the, this guy's power, so e raised to 2.2 power, and that is negative 2. And 10 on the top indicates how many slopes are not zero. That's how they compute. And this goes for all the things right there. And then you you select the one corresponding to the smaller mean square error. Okay, questions? Yes. Okay, so let's see who's next. The model selection. Okay, so let me. Model selection is in 6.1. Okay. So now, what we will do is we will give the output for the forward stepwise selection when we're considering the header's data set. So as a review, header's data set has 19 columns. What they did was, if you look at row 1, the best one component model has been determined to be CRBI. The best, sorry, let me. Sorry, give me 1 second. Let me just make sure if this is forward or a best subset selection. actually happen to be the same. Let's see, what should I do here? Okay, so I'll just change this. Sorry about that. The two graphs are actually the same for best subset selection, forward stepwise selection. So we'll use the best subset here because it will be a bit closer to the exam. So let me start with this plotting output here. What it means, for example, if we were to interpret this forward stepwise selection and we look at this location where it says there's a star behind CRBI, what this means is that CRBI, the variable by itself, has the highest R squared in any single component model. In any single component model. So therefore, the best one. So therefore, the best one component model is intercept and CRBI. So again, this falls in the context of a model selection. This is the result from the best reg subset command. If you run reg subset, you will get this printout here. And then the one star here in the row number 1 corresponding to CRBI. The star corresponding to CRBI means the best one component model is intercept and CRBI. Why? Because it has the highest R squared in any single group. Again, if all the model has size 1, you can directly compare R squared. If the models have different size, then you have to use the adjusted R squared. So that's the difference. So if the question asks, for example, here's a data set. Of course, the exam will not be the headers data set, it will be a different data set, but the idea is going to be exactly the same. If it asks, hey, what is the best single component model? You just go to row 1, see who has the star behind that, and that guy itself, and the intercept are going to be the best one. Okay, questions? Good. Okay, so now let's practice the best 3-component model. So let's duplicate this guy. And then what happens if we were to find? So now it's the best 3-component. So in the best 3-component model, we will go to row number 3. We will go to row number 3, and here you will have the variable hits, you will have the variable CRBI, and the variable putouts. Okay, so hits, CRBI, and putouts. Oh, this is terrible. So hits, CRBI, putouts. Okay, so those things are, and of course the intercept is the best 3-component model. So hits, CRBI, putouts together is the best 3-component model as they have the highest R squared for all 3-component models. For all 3-component models. Okay, so they have the highest R squared for all 3-component models. All 3-component models. So the question will ask, what is the best 3-component model? And the result will be the best 3-component model, the best 3-component model is, of course, intercept, hits, CRBI, and pullouts. Again, the graph here comes from best subset selection. Best subset selection. Okay, questions? So next, let's look at the BIC. Let me determining the overall best model based on BIC. Okay, so the BIC is the lower the better. So the lower one is actually on the top because they're in negative version. So this BIC is smaller the better. Smaller the better. So the items on the top row are so the items forming the best BIC model is or are the things forming the best BIC models are intercept, at HIDS, logs, CRBI, division west, and pullouts. Division west and pullouts. So basically, this is given a graph from the BIC. We make the model selection. This graph here is comparing models of different sizes and of different size models. And once they've been compared, we select the model with the smallest BIC. It's the one at the top, and it consists of intercept, at back hits, walks, CRBI, pullouts, and division west. So this graph right here is to show the winner for each model size. So the difference is the past graph shows the winner for each model size. And here it compares the winners for each model size. So here it's basically saying the best 3 component model is this, but how does the best 3 component model stand among the best 1 component, 2 component, 3, 4, 5, all the way to 19 component models? You have to look at the graph. Okay, so any questions here? Yes?
I was just wondering, are you gonna ask us to compare like the differences between BIC, AIC, CP?
Yeah, so CP and AIC are like the same, at least for model selection purposes. The BIC penalizes the model harder than AIC because a log of n is larger than 2 for most of the sample size. So BIC penalizes a larger model a bit more than AIC. Yeah, do you have to know more than that? No. Yeah, so it's just a very, yeah, I mean, how should I answer the question without telling you the question. Let's say it this way, right? If the thing is on the exam, which it might not be on the exam, but if it is on the exam, the only thing you have to know is, again, it might not be on the exam, right? So if the thing is on the exam, you just have to know that the AIC and CP are the same thing, and DIC penalizes large model more than AIC. That's the only thing you have to know about the comparison of those. What I will focus on is actually the following slide, the comparison for different methods. Those are more important. Okay, for example, when will we use best subset compared to forward stepwise? Those are more important. Okay. Yeah, very good point. Other questions? Yes.
Can you explain what the differences, I guess, with DIC and the slide for the stepwise?
Oh, like what's the difference between this plot and something like this?
Yeah, I understand that, when it shows this is the best one, this is the best one for the two, I guess.
What's the relationship?
Yeah.
Exactly. So what this plot shows here is that what it tells me is that it tells me what is the best one component model by the first row, and that one component model is CRPI. Then it tells me what is the best two component model, which is hits and CRPI. Then it tells me what's the best three component model, which is hits, CRPI, and putouts. So basically for every row it tells me what's the best P component for every row, right? So there are basically 5 informations here corresponding to each model size. So this row tells me, for example, if I want to know what is the best 4 component model, you just go to row number 4. Now, when you have the best 1, 2, 3, all the way to 19 component model, the question is who is the best among the 19 of them, right? And that is answered by this plot right here, which tells you, actually, sorry, there's 20 because there's the one with intercept. And this plot compares the best among the different model sizes to tell you who is like the best among the best, right? So, and then the actual best one is actually the 6 component model too. Right? So the thing previously tells you who is the best model for each model size. This one right here tells you who is the best among all the 19 best models.
So these wouldn't be like the same as in, like, this is a 7? Those wouldn't be the same as like if we had the stepwise a 7?
Exactly. So actually, yes, it should be 6 here because intercept is technically not my handwriting is very bad. So yeah, but it's yes. So if you extend the thing to 6 rows, this will be the 6 things in the table. The table stops at 5, so that's fine. Great. Other questions? Okay. So next, let's go method comparisons. So comparing test subset selection to forward, backward, stepwise selection. Okay. So things like this will be important for the exam because we need to be able to choose the appropriate method. The best subset selection comparing to forward, backward, and stepwise selection is that the best subset selection has the advantage that it does give the best subset for a given model size. So the best subset selection provides the best subset of a given size, a given model size. The best subset selection provides the best subset of any given model size. Then so again, best subset selection by definition, it considers, for example, when the model is of size 6, it considers all possibilities of 6 components and intercept, and it does select the best one based on R squared, and the best one based on R squared. So when does this work? Well, works well when the maximum model size P is small, okay, Why? Because number one, it does give the best model for a given criteria. Given criteria just means like one EIC, etc. And also the computational time is not too high for small p. It's not too high for small p. Let's make it darker. This one's better. Okay, so best subset selection's advantage is that it does select the best subset, which is kind of what the name suggests. And it works well when the maximum model size is small. So if you only want to select, let's say, 5 variables, you can use the best subset selection. Now, the alternative way is let's give a few seconds. Okay, so next, when do I want to use the forward backward stepwise selection? Forward backward stepwise selection. When do I want to use those two things? Well, that is when that's the advantage is the computation these methods are computationally faster, so that's their advantage. Works well when the maximum model size P is large, because large, that just means P larger than 25. Maybe 25 is maybe like 30 or something like that, but let's put 25 there as a placeholder. And then stepwise selection usually gives a good model. It might not be the best, but it's good enough. So the key advantage for forward, backward, stepwise selection compared to best subset selection is that the stepwise selection are greedy algorithms and therefore they're fast. They work well when the maximum model size P is large. Large means like 30, 40, 50. So when P is large, the best subset selection becomes too slow, and stepwise selection usually gives a good enough. Good. So any questions? Usually if something pops up on the exam, I will not make the thing too large, right? Because if the model is too large, you can't print it on the exam paper. So that's why the model is. But again, if a question asks you, like, hey, which method works best in this scenario? You basically, the key idea to look at is whether the maximum model size is big. If the maximum model size is like 40, you must use the stepwise selections because the best subset is just computationally too slow. Right. But if the maximum model size is 5, then there's no reason to use forward backward because checking all possibilities is very fast. So that's the difference. Good. Any questions? Great. Okay, so let's look at the last part. Oh, so when the question might say something like, "What is an example of a brief support?" Right. So, an example could be, let's say, the proportion of variability in y explained by the variability explained by the model is, let's say, 43.2%, because this is the R squared value. It's just some a brief support just means something like this. If the question asks, what is the proportion of variability in y explained by the model? You just say it's 43.2% because this is R squared value. That's it. Right? So, but just don't put the 43.2 by itself because you need some sort of a reason why it's this number. But if you say this is R squared, that's good. Okay, so questions. Okay, so last part was the two distances used for k nearest neighbors regression. So if we have two vectors so let's have two vectors in dimension p. The L2 distance, which is the Euclidean distance, is you square every dimension, sum them, and then take a square root, whereas the L1 distance, which is the Manhattan distance, is you take the absolute value difference and then sum them. Okay, so L2 distance, you take all the pairwise coefficients, sum them, square them, sum them, and take a square root. Whereas the Manhattan is you just take the pairwise difference and add them. On the exam, it will be one of them. It won't be another. Okay, so let's look at an example. Oh, sorry, I think someone didn't have enough time. Good, okay. So for example, A vector equals to 2, 1, B vector equals to the origin. Okay, then the L2 distance between A vector and B vector is the square root of 2 minus 0 squared and then 1 minus 0 squared, which is square root of 5. And the L1 distance of the A vector and the B vector is 2 minus 0 absolute value and then 1 minus 0 absolute value. Okay, and then where do we apply this? This is applied in the k-nearest neighbors. For example, A will be the new point, B along with a bunch of other values that's probably like 5, 0, 0, 5. I'll try to make the numbers a bit more friendly, so all the numbers like 0 and 5 and 10 and stuff like that. When they will be used is one of these distances will be picked on the exam out of those two, and then for a new data point, you find the 2 or 3 closest points and then average y values of those. So that's how this will be used. Good. Any questions here? Mm-hmm.
Lastly, can you get L1 look at something different?
Oh, yes. The lasso also minimizes the L1 norm in addition to the least squares, and then the ridge minimizes the L2 norm in addition to it. The norm is the same, but the concepts are a bit different in the two scenarios. So, I agree with you. Just keep them separate to make life easier. But yes, you're absolutely right. Any other questions? Let me see. I think that's all the review points. We did go over that. We went over that. We talked about the chart. We did the plot. We compared. We support. And then, yes. So that's all the things for this class. Great. So that's the end of the review. Any questions in addition to this? Yes.
Would you recommend us going obviously over this slide deck, but also the midterm 1 and midterm 2?
A great point, yes. There will be very similar questions to the previous two midterms. So I will make a slight modification and then recycle some of them to make sure that, especially the ones that have slightly lower correction rate in the past, you're absolutely right, they will be, you will see familiar questions. And then also, there were 3 free response. The model selection and the graphs and the NOVA are like the last one. Of course, they are material after the two midterms. The first midterm will focus on simple regression, right? So remember the computation for beta 0 hat and beta 1 hat is simple regression, right? So that's like so important that you learn a lot from this final one. So the first question focuses on first midterm, second question focuses on second midterm, and then the third question will focus on this, and something like this, right? So, and the NOVA.
Yeah. Yeah, that's perfect.
Great. Any other questions? Great time to ask. I mean, next Monday I'll ask you. So. Yes.
So question 1 is multiple choice. Is that cumulative?
Yes. So multiple choice. The first part starts with the epsilon, and then it goes all the way to things like this. Right? So yes. So it's cumulative. So again, I don't try to make the exam repetitive. I try to make the exam as short as possible while covering everything. So that's why the multiple choice has to spend everything. Yes.
Will L2 norm and L1 norm be tested explicitly in the exam?
Let's say it this way. Explicitly, no. But will k-nearest neighbors be on the exam? Yes. Right. But k-nearest neighbors requires the one of the two norms. So that's why. But sometimes they agree with each other, but sometimes not. So that's why it's helpful to know how to compute the exact values. Yeah, I won't make it very hard. So it's probably like a 3-4 dimensional thing. It's not going to be too much. And then, yeah. Any other questions? Yes.
Will L1 and L2 norm be tested in the context of ridge and lasso regression?
Great point. The answer should be no, because the ridge and the lasso optimization are too hard and they're computed using the software. So I'll do the ridge and lasso and then provide you with something like this, and you have to interpret the graph. But do you have to do this by hand? It's not possible, I think. So I guess, yeah. So the focus is on the interpretation, not the computation, at least for ridge and lasso. Do you have to know the numbers? Yes. For example, if log of lambda equals to -5, notice the negative sign here. The league variable is estimated on 120. The 120 is something you should be able to read. But will I ask you like how the 120 is computed? No, that's just unreasonable. It's impossible to compute. Right? Yeah. Great. Any other questions? A very good point. You will feel so good after the final exam. It's such a relief. Right? Great. Okay. So thank you for a great semester. So don't forget to come here on Monday. Do not skip that class. If